Hello folks, this is Doug, and in this video we're going to talk about the SN2 reactions, and I'm not going to lie, this is a long video. I probably should have broken up into two, but we're just going to go with it. You can pause, you're big kids. But we were going to talk about all the different facets of SN2 reactions, how we identify them, the different types of nucleophiles and substrates they work with, stereochemical outcomes of them, all those sorts of things. So SN2 reaction, why does it have that name? The N in the SN2, this is a subscript here, not just funny. It is a capital N subscript, and that's just because it's a nucleophilic substitution, and I'll come back and talk about that in a second. The S is the substitution part, right? S for substitution, that's what the S is for. And if you look down at this example right here, right, you can see that the bromine got replaced with this OCH3, this methoxy piece. And so hence the substitution, right? That's all that really happened. You didn't add anything to the molecule. You didn't take away anything from the molecule. You just substituted out the bromine for this new piece, right? So here's the substitution piece. So substitution. And the nucleophilic piece comes from the fact that if you look at this, right, we've got Na plus and we've got OCH3 minus. The piece that got substituted out, right, this OCH3, this is a nucleophile, right? This thing right here is a nucleophile, OCH3 minus. It's negative, and it's got those electrons, that lone pair that can go do stuff, and we'll see the mechanism in a sec. But that's why this is a nucleophilic substitution. You substitute something out with a nucleophile. And then the 2 in this just stands for the fact that this is a second order reaction, that it's bimolecular, right? So second order bimolecular. That means that the rate law, right, if you remember your rate laws back from Gen Chem, so here's a lowercase k for the rate constant. That means that it depends on 2 things, right? It's second order. And it's not one thing squared. In this case, it is 2 different things. And we'll talk about what those 2 different things are in a slide coming up. But it depends on 2 things, so it's a bimolecular reaction. It's second order. So what does this mechanism look like here? It's pretty straightforward in that so if you look at a reaction, anytime you see these ionic compounds, so I have sodium methoxide right here, like I was saying on a previous video, always take your ionic compounds and always split them up, right? So I want to think about this as having an Na plus and an OCH3 minus, right? So I'm using this same example as I had on the previous slide. And we already talked about how I know that the Na plus is not going to really be doing anything. I don't need to worry about it because those are just spectator ions, right? Those alkali metal ions, they're just spectators. So spectator, I can spell that probably. Spectator ion, it's not going to do anything. And like I was just saying before, my OCH3 minus here, right, that's going to be a nucleophile. And if I go over to my bromopropane here, anytime you're not sure what reaction is going to occur, I always recommend you put all your charges out there and start seeing what the charges want to do, right? So if I look at this, I see I have a polar bond between the bromine and the carbon. So bromine is a minus. That carbon right there is going to be partially positive, right? Just because bromine is a little more electronegative than carbon. Now, right off the bat then, I see that I've got a positive charge here and I've got a negative charge on my O. So my O is going to be attracted to that carbon right there. And so I need to draw a line, right? Remember that your mechanism arrows, all of your arrows in OChem, whether it was the acid-based stuff or this new organic stuff, it always goes from higher electron density to lower electron density, right? So this is your higher, some higher electron density. You go from the most electron-rich to electron-poor, higher electron density, and then this spot right here, right, has lower electron density, right, because it's partially positive. So that means then my mechanism arrow would be from the lone pair to that partially positive carbon. But that carbon can't have all of those bonds, right, because there are 2 H's there, so it can't have 5. It's going to kick out our leaving group, the bromine, because the bromine is going to be really stable when it comes off. And I accidentally wrote over here chloride. I don't know why, but it would be bromide. The bromide is going to get kicked out. And I want to look at that in a little more detail here. Now, I drew the arrow just kind of coming from this direction, but I could have drawn the arrow coming from this way, or maybe I could have drawn it coming from this side, or I could have had it coming from this side. And this is getting really messy, and I apologize for that, but it's kind of intentional, right? There is only one correct way that this nucleophile is going to approach this molecule. And I'm not too sure how much you all remember of your molecular orbital diagram stuff, but you may remember, right? So if you look at the MO theory, so molecular orbital theory, that if I look at this CBr bond, that its sigma molecular orbital between the carbon and the bromine, that's going to look something like this, where you had two orbitals with lobes that overlapped so that they make some sort of great overlapping spot. I'll leave that unshaded. And then they're going to have two lobes on either side that are shaded, right? And that would be for your sigma, which is going to be filled. That's going to have the two electrons in it. But you're also going to have your sigma star. I'll draw a carbon, bromine. I'll do this in a different color, do it in purple. Where sigma star is where those two orbitals overlapped, but they overlapped deconstructively, right? With the sigma bond, they overlapped constructively. Here we're going to have them interact destructively so that you get something that looks more like this, where this is shaded. You got a little lobe of an opposite color, a little lobe of the opposite, and then a big lobe of the other piece. So you got your sigma star. And the idea with the sigma star is that that's empty, right? I'm not putting two electrons in there. And when you're going to break this carbon-bromine bond, the idea is that your nucleophile here, your OCH3, right, your OCH3, it's going to put those two electrons that it's right acting as a lowest base, it's going to put those two electrons into the empty sigma star. And so if I superpose that sigma star onto that bromopropane here, what that's going to look like is that here's that big back lobe, and then the lobe, and then a lobe, and then the other lobe, right? Here's all the empty spots, right? Here's that sigma star, right, that I drew in purple. Here's that sigma star superposed over that carbon-bromine bond in our substrate. And what you'll notice here is that there's not very much electron density. Yeah, let me do this. So there's not very much electron density in between, there's not a lot of empty orbital that is in between the carbon and bromine, right? These are little lobes, not big lobes. Plus the problem is that there's already electrons here, right, from the sigma. There's the electron density here, actually in this spot. And yes, there's a big lobe right here, but you also have a big old bromine there, which is in the way. It's overlapping where the bromine is. So you got this big old empty orbital, but there's a bromine in the way. But what you see is that the other lobe of this sigma star is right here where there's nothing, right? Like in this case, there happen to be two H's nearby, but they're not really in the way, right? There's an H coming out, an H going back, but they're not really in the way there. And so what that means is that this OCH3 or any nucleophile is always going to be able to enter, it's going to be able to attack that carbon-bromine bond from what we call the back side, right? This is what we call the backside attack. So backside attack. Your nucleophile is always going to attack from the opposite side of the leaving group, in this case bromine, but it could be chlorine, it could be some sulfonate ester we'll see later, could be iodine, whatever. It always comes from the back. And when it does that, right, it puts those electrons into the sigma star, which is an anti-bonding orbital. And because now you have the same number of electrons in an anti-bonding orbital as you do a bonding orbital, the bond breaks, which is why we draw our second arrow where that bond has broken. And that's how we get to, right, the OCH3 being on here and the bromide having popped off, right? The bromine came away with those two electrons. So we're able to do the backside attack and replace that bromine with the OCH3. And I'll draw the mechanism in a little bit cleaner way in the next slide, but it's basically just one step. Let me show you. So if I was to do that again, I'm going to clean this up a little bit here. I'm just going to have my OCH3. Right, it has a minus, partially negative bromine, partially positive carbon. I'm going to have my OCH3 attack from the backside of the bromine and then kick out the bromine, just like that. That's all we're going to do. And it's only this one step. And so if you're drawing an energy diagram for this, right, so here's your energy. Here's the reaction coordinate down here on the right, your reaction progress. You're going to start with your starting materials. You have your products. It's going to be lower in energy, PDT for product. It's just going to be one hump, that's it. There are no intermediates. There's this transition here. We have a transition state right here, where what we're seeing is that this is supposed to show that OCH3, right, that's coming in from the back side of where the bromine was, right? So this OCH3 is coming in from the back side of the bromine to kick it out. This is the in-between. These dotted lines right here, that's not supposed to be dotted like a dash, like meaning going away. That dotted is supposed to be not quite a full bond, but not no bond. It's the in-between, right? Like every transition step, like every transition state. It's just the in-between, right? So this is the bond being made. And this is the bond being broken. And what I need to add here are the charges, full or partial or whatever, right? So before we had oxygen being fully negative, but at the end, it's not fully negative anymore. It's just partially negative. So that means the oxygen in the transition state is no longer fully negative. It's got to be partially negative. So I'll go ahead and I'll put a partial negative there on that oxygen. And if I look at the bromine, here it was partially negative, but at the end, let's see, I copied and pasted that. Not chloride, doesn't come out of nowhere. We're not breaking any weird laws of thermodynamics. The bromide here has a negative charge at the end, right? So it goes from not having a full negative to having a full negative, which means that the bromide in the transition state must be somewhere in between those. So that must mean it is also partially negative, is the idea. And so the OCH3 is coming in from the backs of that bromine and breaking it off, right? And so if I'm going to go down here and I'm going to label all of this, the only thing I need to label on my energy diagram is that this is the transition state up here, right? No intermediates, just the transition state. And if you don't remember what that double dagger thing is, that means transition state. So transition state, right? They're not isolable, and they're when you're making and breaking bonds. They're high energy transitions. So transition state, that's what that means. That's what that double dagger means. And that's why I put that, drawing where I used all the green writing, that whole thing in square brackets with that double dagger, that means transition state. So it's just one step here. And we'll see how that differs from SN1 reactions, which have at least 2, sometimes 3 steps. So that'll be in the next video. But real straightforward reaction. You have one set of arrows, no intermediates. It's just boom. What that means is that another piece of vocabulary that you're going to want to use is that this is a one-step reaction. So one-step reaction. And the term you'll hear for that is that it's concerted. That means that it's just one step. It's a concerted reaction. You'll see that E2s are also going to be concerted. They're also going to be one steps. But like I was just saying, SN1s are multiple steps. They are not concerted. And also in this, so I might as well put this here too, since it's one step, both the nucleophile and the substrate will affect the rate, right? If you have more bromopropane, you're going to have more collisions with the nucleophile. So that means the more bromopropane you have, the faster the rate goes. Same thing with your nucleophile, right? Since it has to hit your bromopropane, it has to hit your substrate. The more nucleophile you have, the more collisions you have, the faster the rate. So if you look at the rate for these, right, the rate, like I was saying before, the rate is bimolecular. It's going to depend on both the amount of substrate that you have, right, that's your alkyl halide, and it's going to depend on the amount of nucleophile that you have, right? The more of each of them you have, the faster the reaction goes, because both of them are in the rate determining step. Both of them are in the slow step, or in other words, and that's because there's only one step in this. Now, the substrate limitations. Remember on that previous slide, we had to come in and do that backside attack. And so my nucleophile needs to be able to get to that backside. It needs to get to that sigma star lobe in the backside of whatever your leaving group is. So if I take a look at things like this first one, well, let me just write out what I just said there, right? The nucleophile needs to be able the backside. The backside of where the leaving group is. And so that means, for example, with this bromine thing here, right, partially negative, partially positive, that means I got to get to that carbon, and that my nucleophile needs to be able to approach from the backside, from the bottom side. But if I take a look at this, one of the things that's not great about these skeletal drawings, these zigzag drawings, the line bond, the ultimate, whatever you want to call these zigzag structures, is that it doesn't let you see all of these H's. And so if I start to put all of these H's in here, hopefully you'll start to see pretty quickly. Right, I'm just doing them on the carbons that are attached to there. There's a lot of stuff in the way. There's a lot of H's in the way. So it's hard, right? If I'm going to have my nucleophile try to get in here, it's going to start bumping into these things, right? This is too bulky. I can't get to here. And if you take a look at this, right, this is a tertiary substrate. And tertiary substrates are just too bulky. We cannot have an SN2, so no SN2 reactions for tertiary substrates. There's too much there. I can't get to the backside there. Can't happen. Now that's in contrast, right, to the next one with the iodine. This is just a primary. It's a primary substrate, right? If I look at this, really I've got H's here. Right, I've got H's on this carbon, and I've got the two H's that are here, but that's not too bad at all. That's not nearly as much stuff as what was on that first one, right? So now if I have a nucleophile that needs to attack, there's not that much stuff in the way. Oh, sorry. There's not that much stuff in the way, so it's easy for it to get to the backside. So you can do an SN2, and in fact, primary substrates do SN2s really well. You can do an SN2 reaction on that. It works great. Same thing for a methyl, right? You have a methyl here. Methyl substrate, that's the best, that's the fastest, right? There's only H's there. Methyl substrates are really great for SN2 reactions. It's very, very easy to attack them. And in fact, that's one of the reasons why methyl halides like iodomethane or bromomethane, that's why they're really toxic to us, because all of the little nucleophiles in us, right, like our DNA, it has a bunch of nitrogens on it, stuff like that, all the sulfurs in us. Those are all good nucleophiles. As soon as you throw in like methyl bromide, that attaches, all of our nucleophiles in us attack it, and then they bind, and when it binds to like your DNA, for example, it can give you cancer because it screws up the translation, transcription, and all that sort of stuff. So this also plays a role in why some of these molecules are toxic. If they're really, really, really good SN2 substrates, they're really toxic to us. This one here is secondary, which is kind of in between. They're pretty slow. They do slow SN2s. You can have good nucleophiles in the work fine, but they're much, 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 much slower than primary or methyls. And then here's another tertiary, which we showed is no good, and here that's primary, which was good. So if I just come back here with big red marks, for the tertiary one, no. For this one, yes, yes, sort of, no, and yes, right? So secondaries are going to be kind of so-so, and I'm going to put this all on a chart later. The big key point here is that for SN2s, you have to get to the backside, so you cannot be a very bulky, a very hindered substrate. Now, the stereochemical outcomes, right? On that previous slide, and I'd go back, but it screws up the way I record. On that previous slide, I didn't have any chiral centers, right? Where that bromine was, if you go back and look a couple seconds ago, there was no chiral center, there was no RNS configuration, nothing. So I didn't have to worry about this. If I have a molecule like this one, if you take a look at this, what we can see here is that this molecule, 1, 2, 3, so at 1, 2, 3, it looks like it is S, right? This is an S configuration, right? We have a chiral center here, that's chiral. I need to pay attention now to the stereochemistry, because I want to know, is the product that I'm going to make also still going to be S, or is it going to be R, or is it going to be a mixture of R and S? Like, what's going to happen during this reaction? If you haven't seen it before, the D right here, that stands for deuterium. The D is for deuterium. That's just an H that has a neutron, right? Normally hydrogen doesn't have a neutron, it only has a proton, but deuterium, capitalized, it's a capital D, or you might see a 2 superscript in front of an H because it's just an isotope of hydrogen. So it's like hydrogen, but it's a little heavier, so that means it has a higher priority. So when we do our priorities here, bromine is 1, carbon is 2, deuterium is 3, H is 4. Lowest priority group in the back looks like counterclockwise, so it's S. Now, in this example, I've got a bromo. I've kind of got a similar molecule, but I have a deuterium in here now, so I have a chiral center. If I look at my nucleophile, I'm going to do what I always do with my nucleophile, which is split this, ignore the K, and then I have the S thing. So I have a CH3, a CH2, and this S minus. And like I said, we're always going to do a backside attack, right? We're always going to do a backside attack because that carbon was partially positive, the bromine's partially negative. And when I do the backside attack, I get this intermediate here, right? I'm going to get this intermediate where, or not intermediate, excuse me, transition state, where the sulfur group is coming in from the opposite side of that bromine. It's coming in from the opposite side of that bromine. And remember, that's what's happening here is that this bond down here is being made and this one is being broken. And so right after this, the molecule is going to kind of look like this, right? Where I've just made that new bond with the sulfur, and then the bromide gets released. Let me draw those electrons so we're super clear, right? It had 1, 2, 3, 4, 5, 6 lone pairs. Now it has 1, 2, 3, 4, 5, 6, 7, 8, right? It got the 2 electrons that were here. Those are its 2 new lone pair, or its new lone pair. But what's important here is that the sulfur group is opposite of the bromine group. It's replaced it, right? And that comes back to what we were saying on an earlier slide, is that you have a backside attack. But when you have a chiral center, this backside attack always leads to an inversion of stereochemistry. An inversion of stereochemistry. So now the nucleophile should be in the opposite place that the leaving group was, in my case, bromine. And I should just go double check. I'll go up here and make sure that so that means I should go from S to R. Or if I'd start off with R, I should go to S. And so if I do this, right, sulfur weighs the most, carbon weighs the second most, deuterium weighs the third most, hydrogen weighs the fourth most. So my lowest priority group's in the back. That's great. I go 1, 2, 3. That's clockwise. That means that this is R. So I did draw the right molecule, the right stereoisomer, specifically an enantiomer in this case. So SN2s are always going to do this backside attack. So if you have a chiral center, you're always going to get an inversion of stereochemistry. That means S to R or R to S, right? It's not going to be a mixture. We'll see SN1s, they scramble it up. The SN1s give you 2 products. They give you 2 enantiomers or diastereomers, and they're going to be a mixture of R and S's where you reacted. So that's very different. SN2, always an inversion, always an inversion. So here's kind of a summary, and then I have to talk about a little bit more stuff, right? So we just said that SN2 stands for nucleophilic substitutions. It's second order. It's that bimolecular thing. Since there's only one step, both the nucleophile and the substrate matter. For the nucleophiles, and I'm going to talk more about this on the next slide, nucleophiles, I need good nucleophiles that are smallish. I can't have really big hindered ones, right? If they're really bulky or have a whole bunch of like tertiary groups or something like that, that's no good. My substrates, we kind of talked about this. Fastest with the unhindered ones, right? So really fast with methyl or primary. Secondaries are okay, but tertiary is too hindered. It's just too slow for tertiaries. You're not going to see SN2 reactions with tertiary halides. And then the stereochemistry, if you have a chiral center, then we're going to get an inversion. That means you're going to go from R to S or S to R. And solvents, I'll do another video, a whole other video on solvents, but I might as well put this here now so that you can compare and contrast later. For solvents, SN2s tend to go faster in polar aprotic, and that's important, the aprotic solvents. So like dimethyl sulfoxide, DMSO, or acetone, or tetrahydrofuran, THF, other aprotic but polar solvents. Now what I'm going to do in all of these videos for the SN2, SN1, E2, and E1 is I'm going to keep coming back to this chart. And I have a handout of this posted online, but I wanted to make this with you all also because I think it's good to think about. So what I'm going to do here is I've got 2 sections, right? I've got the substrate section here on the left, right? I've got all this substrate section on the left. And then I have a nucleophile and bases piece on the right-hand side, right? So these are the 2 pieces you're going to be reacting. You're going to take some sort of substrate, some sort of nucleophile and base. And we just talked about SN2, so let's put that on this. We just said that SN2s do work great with methyl because they're so unhindered, right? So SN2s, they're so unhindered. Methyl halides can absolutely do SN2s. For primary, also super unhindered, really easy to do primaries. Now I'm going to leave a comma after this because I'm going to put another reaction in here. And what I'm going to do is I'm putting these in order of how quickly the reactions occur, right? So you have a sense of which one's faster or slower so you can predict major products more easily. Now secondary, we said secondaries can do SN2s, but they're slower. So there's actually something that happens faster than SN2s. And there's going to be something that happens slower than SN2s. So for secondary substrates, the SN2s are going to fall in the middle of my SN1, SN2, E1, E2 reaction suite. And then tertiaries, we said two-hindered, not going to happen. So I'm just not going to put SN2 there at all. It's not going to happen. Now, when I look at my substrate or base, right, let me put some examples down here so we have something to talk about. Let's put hydroxide. Let's put bromide. And let me put lone pairs so we can all see the same thing. Let me put water. Make that a little bit prettier. H2O. Let me put T-butoxide. And let me put maybe acetate. I think those would be good. Let's put those. Now, the first thing I want you to see, if you see these molecules, you should be able to figure out, are they poor nucleophiles or good nucleophiles, and are they strong or weak bases, and are they hindered or unhindered? When you look at these, if you can do that, your job is going to be so much easier when it comes to these reactions. So poor nucleophiles, good nucleophiles. For the most part, broad brush here, poor nucleophiles tend to only have partial negatives. And generally speaking, not always, but generally speaking, good nucleophiles tend to be fully negative. That's one easy way to kind of split stuff up pretty quickly. So if I want to see an example of a poor nucleophile here, the only poor nucleophile that I have on this list would be water, right? Because all the rest of these have full negative charges. So water would be a good example of a poor nucleophile because it only has that partial negative right here. So as an example of a poor nucleophile, I'm going to put water. And I'm also going to put the alcohols, since they're very, very similar to water, right? They react really similar. They're the same basicity, acidity, essentially, same nucleophilicity. They're about the same, right? They don't have full negative charges. So I've taken care of water. Check. Now, the rest of these are going to be pretty good nucleophiles, depending on their size. So they all have full negatives. So I'm going to put them in this other camp. I'm going to move down this chart. The next thing is deciphering what's a weak base versus a strong base, right? And so remember that weak bases are going to be anything that is more stable than hydroxide. So more stable than hydroxide. Strong bases are going to be anything less stable than hydroxide, right? Hydroxide is going to be about our standard. So hydroxide is a strong base. Anything more stable, anything weaker than that's a weak base. So that means of these, I actually have two, right? I actually have two that are more stable than hydroxide. The bromide is definitely more stable, right? So good examples of these would be the halogens, right? So like Cl minus, Br minus, I minus, etc., fluoride. But also things that are like, here's an example of something that's more stable, right? Here, the acetate, that's resonance stabilized, so that's also more stable than hydroxide because that negative is delocalized between two different oxygens. So that's also a good nucleophile, but it's a weak base. And then for our strong bases, right, the rest of these are going to be strong, I just need hindered and unhindered. And by hindered and unhindered, I mean unhindered are pretty much things that don't really have branching at that point of attachment, versus hindered things have branching at the point of attachment to the basic atom or the nucleophilic atom. So unhindered would be things like hydroxide, which we put, small alkoxides like methoxide, ethoxide, maybe NH2 minus, stuff like that. Oh, weak bases, I should also put up here the S minus, because remember the sulfur is larger than oxygen, so it's better able to handle that negative charge, it's lower in energy, it's less basic. So unhindered, right, those don't have a lot of branching on them. Versus hindered would be things like this T-butoxide, right? Hindered would be something like the T-butoxide, right, where it's a tertiary carbon right here, and you've got methyls. Or things like, one of my favorites is going to be LDA. So LDA stands for lithium diisopropylamide. But that's a nitrogen with 2 isopropyls on it that's negative, right? So it's a strong base because it's a negative nitrogen. That's a less electronegative than oxygen, so it's higher in energy. And it's bulky because it's got 2 isopropyl groups on it, right? So it's a real big boy with this LDA. Now, let me write out the name. Lithium diisopropyl. I'm running out of room. Sorry, I can't handle that. Let's try that again. I'll start way over here. Lithium diisopropylamide. Lithium diisopropylamide. A great example of a strong base, but it's very hindered, right? It's not very stable, but it's very bulky. So here's just some examples that go in these different categories. And again, we want to come back and think, well, what can do an SN2 reaction? If I look at my poor nucleophiles, they're only partially positive. So they're not really going to have that strong of an attraction to an electrophile. We need that strong attraction between our nucleophile and that partially positive carbon on our substrate. So this just is not going to have that. So we don't see poor nucleophiles do SN2s very much. Maybe in like a solvolysis where there's like a cajillion equivalents of one of these, but in a 1-to-1 ratio, it's not that strong. It's going to be super, super, super slow. So really just our good nucleophiles. So these good nucleophiles that are weak bases, these are great, right? I did some of these examples. I used a hydroxide-like thing. I used a sulfur-like thing. These are great at doing SN2s. So I'm going to put SN2 for those. And our strong bases, these also will have great attraction to the substrate, right? Full negatives down here with the OCH3, the hydroxide, the NH2. These also can do SN2 reactions. But the hindered ones, they're too big. They're too big, too bulky, can't do SN2 reactions, can't do that backside attack. They're going to bump into things, make that transition energy too high, too slow. So realistically, the things that are best at doing SN2 reactions are the good nucleophiles that are weak bases and the good nucleophiles that are strong bases but small. They're unhindered. So those are our 2. So we're going to match those up in a little bit. So let's see some examples. So here we go. Now if I take a look at these, I'm going to say, oh, this is a primary halide. And this is a strong base, right, because it's hydroxide. And it's unhindered. It's small. Right? There's no branching. It's just OCH3 minus. So I've got my Na plus. I've got my OCH3 minus. And I know that both primary substrates and small unhindered bases can do SN2 reactions. So again, all I need to do is say, okay, well, my chlorine's partially negative. This carbon's partially positive. I'm going to have my hydroxide attack the backside here. There is no chiral center there, so I don't really need to worry about where I place. Oops. Where I place. That's going to happen a lot, by the way. Sorry. It doesn't matter where I place on this carbon the hydroxide. I'll just put it in the same spot because there's no chiral center. There's no RNS, no inversion or anything like that. And that's my product. For those of you who really like to balance equations, knock yourself out and put the Na plus and Cl minus. That technically is the side product, but this is organic chemistry, so I just care about the organic thing. I just care about the thing that has the carbon in it. So I just want to see the alcohol. I just want to see that piece. Now, if I look at the second one, and this is actually a good time to like pause. Why don't you pause for a second and see if you can do these last 3. One of these is not going to do an SN2, but the other 2 will. So why don't you pause for a second, see if you can take a crack at the last 2 and draw the products for them. Okay, hopefully you paused, looked at these. Now, this one, second one's kind of weird because I have 2 bromines here, right? This bromine is at a primary carbon, right? This is a primary alkyl halide, which is a great SN2 substrate. But here, this is a secondary carbon. but we treat it as tertiary because there's no hydrogen on it. It's like it's bonded twice. But the bigger problem is that it's not alkyl. Right, remember that alkyl are sp3 carbons. This is sp2. You're not going to do an SN2 reaction on an sp2 or sp hybridized carbon, right? These reactions that we're talking about in this chapter, they're only going to work on sp3 carbons. That's what we're focusing on. That's what you're going to see. So if it looks like it's on an sp2 carbon or something hybridized like that, not going to work. Don't even look at it. So I'm just going to kind of ignore this one over here. That's not an option. And look at this and say, okay, well, I've got a negative O right here. So that negative O is going to be attracted to that partially positive carbon right there. Kick out the bromine. And my product should look something like this. Bromine is still hanging out here. I didn't touch that one. But this one now, this carbon, now I have an O and with the acetate piece, right? So this carbon got attached. Now there's an O there. And then technically, there's an NaBr floating around somewhere, right? Those ions are floating around. And this would be my product. And I'm drawing in blue the mechanism of these reactions just because it kind of helps me see what's going on. If I just ask you what the product is, I don't need to see the mechanism. I will ask you specific questions on quizzes or tests or quests or something like that where I do want to see a mechanism. I'll say, draw all the arrows, draw all the lone pairs, and I want to see all of that stuff. For these, I just want to know. I just want to know the product. For this one, we've got the NaSH. So that means I've got an SH minus. And I've got a partially negative carbon here, partially positive here. Now this is a secondary, which means it's going to go slower, but I've got a negative sulfur, which is a great nucleophile. So it's going to be fast enough that I'm going to go ahead and do this. One thing to notice on this one, though, is that it is chiral. Right, I do have a chiral center in this one, so I need to pay attention to my stereochemistry. And remember that it's an inversion of stereochemistry, so you just need to put it in the opposite place. If I draw the mechanism for this, right, sulfur backside attack, chlorine kicks out. If I want to make sure that it's in the opposite place, one trick is to just simply draw it on the same carbon, but with the opposite dash or wedge configuration, right? So it was a wedge. Now I'm going to draw it as a dash. So I know that I've drawn the enantiomer. I know that I drew it opposite. I know it doesn't look from this drawing that it's opposite, but I promise you that it is. It's opposite. And you can double check by looking at your configurations, right? So for the first one, it looks like it's R. And for the second one, it looks like it is S, right? Because I have 1, 2, 3, but my lowest priority group is in front, so I have to take the priority and switch it. So it looks like it's R, but really it's S. And so I did draw the right enantiomer there. And then lastly, for this one right here, this is a tertiary carbon, which means right off the bat, I cannot do SN2. So no SN2 reactions. So we're just going to ignore this one for now. I'm not going to put no reaction because that's a lie. It's going to end up doing an E2 reaction, but we don't know that yet, so just ignore that. What I want you to get from this right now is that it's not going to go the SN2 route. It's not going to be an SN2 mechanism because tertiary halides are too bulky. Nucleophile can't get there. So that was my long video. I hope that wasn't too long. I tried to talk kind of quickly. You can go back and re-watch whatever I went over too fast. But that's what the SN2 reaction is. And so what we're going to do in the next video is we're going to compare that to the SN1 reaction and then the E2 and then the E1, talk about solvents. So that's the plan. So study up, watch the next video right now. Make sure you have good notes. Happy studying and good luck.